Okay, for today, when we'll attempt to solve the MDP, that is to find a policy that maximizes our expected utility, we'll assume that the MDP model is known. We know the transition, we know the distribution over the outcomes. That is, we know the expected reward, and we know the expected next state from being at any state and taking a specific action. And we know that for any state and action in our environment. This is not a practical assumption, but it will help us get started. So we'll see some techniques that we can apply to optimize pi, the policy, in this setting, and we will later see how we can first generalize these techniques to apply also for the case that this assumption is dropped. By the way, if we would assume the same, that is to know the model of the problem for the bandit case, this will directly imply the optimal policy, right? What would be the optimal policy in that case, Bob?
Taking the slot which gives you the highest reward most often.
Right. So you'll simply play the action that has the highest expected reward, right? So this assumption simplifies stuff definitely for the multi-round bandit problem, but it does not directly imply a solution for the more general MDP, and we'll see why that is the case. We'll still need to do some computations in order to solve the MDP, and when I say that, I mean to compute the optimal policy. Why is this not the case for MDPs? So, okay, can you think of? I just said that knowing the model even if you know the model, it's not trivial to imply the policy for an MDP, the optimal policy. Why is that? Can you think of that? So why can I do what you just said for the bandit case? That is, when I'm in a state, I know the outcome for each action. I'll simply pick the action that provides the highest expected reward. Why can't I do it for MDPs? Oh, I can do that. But why won't that imply the optimal policy for an MDP?
Because an action that might, at the current state, seem like the best, but in the long term, may not give the highest returns.
Right, because
now there are many states.
Maximizing the reward that you're gonna get at the moment might not be a good strategy to optimize future reward, right? And to getting to more lucrative states. Yeah, that's the case, and that is what makes solving an MDP slightly more difficult, right? Okay, so let's see some examples of MDP formalization for different problems. So previously we saw it for the grid world, where the robot is just moving around, but of course, for any problem that we are trying to solve with RL, we'll need to define the relevant MDP, and you need to do the same for your course project, right? That is, you need to define a state, the state space, the action space, the reward function, and state transition probabilities. Okay, or how are they stochastic? That's pretty important. So, for instance, if we would like to train an autonomous car to drive, we can say that the state space is simply the images from a front-facing camera. But this is a low-tier autonomous car, I guess, without a lot of sensing equipment. So let's say we only have a front-facing camera, so that will define our state space. Our action space might be steering, say in some range, from -1, that's the far left, and to 1 will be the far right. And we might include acceleration from 0 to 1, just normalized, and braking from 0 to 1. Of course, different autonomous vehicles might have different actions and state space. Okay, it's just an example. And for the reward function, we've seen this before. You can define it in various different ways. For instance, driving off-road is -10, hitting or crashing into someone is a very negative reward, and so on. And as I said previously, designing a reward function is not trivial, and sometimes if you misdesign it, you get unexpected behaviors that might optimize the reward function that you defined, but are not exactly the behavior that you intended for. So a lot of time it's a trial and error thing, and there are some theory behind designing correct reward functions. We might discuss some of that later on. Then we'll also need to define the state transition probabilities, or at least that the state transition is a stochastic process. Else, as I said before, reinforcement learning might not be the best solution for the problem. Okay, so in the case of autonomous driving, this might be defined by stochasticity in actions outcome and other actuators in the road, I don't know. Other drivers or some frictions or some stuff in your engine that has some randomness to it. Okay? Let's look at another example. Let's say that we're looking at a robot locomotion environment. So the state can be in this case the angle and position of joints, obstacles and pits in the environment. Actions in this case can be the torques applied to the joints. The reward might be the forward speed. I think in some of these they also, in many cases people define it also as standing upright and moving forward. Else the humanoid does some funny stuff, right? Like jumping around on the floor.
Standing upright.
Some reward, right. So this goes back into some reward design, as I said previously. Just placing a reward that sounds correct might lead to unintentional behavior, some behavior that you didn't expect, which still optimize the reward function, but not what you expected. So in some cases we go back and tweak the reward function accordingly. This is the case for many times the humanoid environment in the robot locomotion. And the state transition probabilities in this case will be defined by stochasticity in the actions outcome, if we'll assume some noisy engines, and the obstacles and pits in the environment, unknowns in the environment. Another example that we've seen before would be for video games. The state space can be defined by raw pixels. So, right, that's the example that we've seen before. Actions would be, okay, and I'm guessing you can see how raw pixels can represent a state. Raw pixels is just a matrix of values, right? So it's very high dimensional state space, right? Each state is very high dimensional, which seems like a no-go, but how do we address such high dimensional state spaces?
Using neural networks.
Right, we'll use deep learning to handle such complicated high-dimensional state spaces or states. We'll see that later on, right? We'll first need to cover the basics before getting there. The actions in the video game domain will be the game controllers. The reward is simply the change in the score, in the game score, or you can define it as just the score at the final when you finish the game. Right? This is known as a sparse reward, which has some issues affiliated with that. So actually, in most cases, you would like to provide your RL agent with with better guidance throughout the game, right? You show him, hey, you did something right. The score is increased. Although what you really care about is increasing the score at the end of the game, it helps learning a lot if you provide more guidance as reward during the learning, during the interaction with the environment. And then the state transition probabilities in this case will be defined by stochasticity in the game evolution. So we've discussed this specific game before, right? The breakout domain here on the right. And I'll just remind you that this game, if we just include one frame of the game, the current frame of the game, this is not a Markovian decision process, because history, previous states, previous frames will determine the velocity, the velocity vector of the ball, which is very important in order to optimize your policy and in order to define the transition probabilities for the next state. And so, as we've seen before, the authors of this paper address this issue by including the four last frames of the game, and by doing so, they made this specific game Markovian. The MDP for this specific game Markovian. Okay, another example that we've previously seen is the traffic signal control, where the states can be the current signal assignment, green, yellow, and red assignment for each one of the phases, and then some sensing assumptions of incoming vehicles. For instance, contemporary sensing equipment can tell you the number of approaching vehicles, accumulated waiting time, number of stopped vehicles, and average speed of approaching vehicles on each one of the incoming lanes. So this can represent your states list. Actions in this case will be the signal assignment, so which phases get a green assignment, which get a yellow assignment, and which direction gets a red assignment. The reward can be reduction in traffic delay or the throughput of the intersection, or there are several variants here. But the reduction in traffic delay can be a reasonable reward. And the state transition probabilities are defined by the stochasticity in the approaching vehicle domain. How many vehicles are coming to the intersection, and sometimes the speed of the vehicles. Each driver has a different speed. Maybe there's slight deviation in the trajectories, accidents, and so on. There's a lot of stochasticity in this environment. Questions? No. Okay. Next, let's define the MDP, our objective when trying to solve an MDP. What do I mean by saying that we're solving an MDP? What would it be to solve an MDP? So in order to solve an MDP, we would like to compute a policy which map states into actions. So it will tell us what action to take in every state. Okay, so the policy is a function. More specifically, we would like to compute the optimal policy. That is the policy that results in the maximum expected reward when we start from our initial state. So the optimal policy is denoted by pi star. We would like to find or to compute pi star, and we'll see different approaches to do that. Right? See a lot of different ways to compute pi star. So how can we quickly define pi star, given the definition that I just provided? So mathematically it would look as follows. Pi star is the action for each state. It should return the action that maximizes the expected immediate reward, right? What is the expected immediate reward? As we saw previously, following the definition of an expected value, it's the summation of all possible rewards multiplied by the probability of observing that reward. Okay, this is just the definition of an expected value. However, this is not enough, as we said previously, right? This might be enough for a multi-armed bandit problem, but this is not enough for an MDP, because we also are required to optimize over the future, the next steps, right? And so we have, for those of you who already took the Introduction to AI course, we have an expectimax tree that goes on, well, until the end of the episode, until the end of the MDP. So we need to include that in our definition. So we would like to, our optimal policy, pi star, should return the action that maximizes the immediate reward, plus the expected future reward, all of the rewards that we're going to observe from the next state onward, right? And we define the sum of expected reward that we're going to encounter as G. Of course, we'll have to take the expected value of G because there is stochasticity in the environment. So each time we we do a rollout, we continue to follow a specific policy, we might see a different set of rewards. And so we would like to optimize the expected value of those sum of rewards. So this is also known, so the expected sum of rewards from being at a specific state S prime and following the optimal policy pi star is also denoted in the literature, commonly denoted as V star of S prime. So V star is just a function. It's very similar to the Q function that we've seen previously, which maps state and actions to the expected sum of rewards that we're going to observe after being at a specific state and a specific action. So the state value is a generalization of that does not take into account a specific action. So it does kind of take into account a specific action, but that would be the A star, the action that follows the optimal policy. Yes, a question.
Yes, Professor. For an MDP, would the optimal policy be unique?
Not necessarily, right? So there might be various optimal policies. There are some cases where it's not only not unique, in some cases it's not even deterministic. That is, in a specific state, the optimal action to take is to throw a dice and pick with some probability different actions, right? Can you think of an example for such a domain? By the way,
Like
it's an interesting question. So,
like in the casino?
a domain, right? So a domain where the optimal action to take in a specific state is a distribution of actions, right? So, so that's right. So, for instance, if you're playing poker in a casino, for the same hand, you don't want to always play the same action, else you allow your opponents to know what you have in your hand, right? So actually the optimal strategy to play poker is to bluff sometimes, right? And this can also be, this notion is also, can also be observed in algorithmic game theory, where a Nash equilibrium does not necessarily always exist in all kinds of normal form games. For those of you who already went over Introduction to AI, this might make sense. For the others, don't worry too much about that. But there is a proof that in all normal form games, there must exist a mixed Nash equilibrium. So there is a mixed strategy that does result in a Nash equilibrium. Don't worry too much about that. But just to answer your question, no, there's not necessarily a unique pi star. And then this might go back into the objective that I discussed at the beginning of this slide, which I said our goal is to compute the optimal policy. And you might say, okay, so is our objective to compute all optimal policies or just a single one? So usually it's just a single one because, hey, you know, we want to act optimally. We don't care how we act optimally, right? Or in a specific way to act optimally, if we cannot distinguish between them, of course, given our reward function. However, we will see later on approaches that are called maximum entropy approaches. We'll define that later on, max-ent approaches, that do try to say, hey, you know, if you have several optimal modes of optimality, optimal ways to act, try to cover all of them. Because this is actually important for efficient exploration, because the idea is that allows you to truly detect the true optimal policy. So again, I don't have a straight up answer, but all of my answers are usually, that will usually be the case. It depends, right? That's usually the case with science. Okay, so let's define some notation, or let's just reiterate the notation that we just discussed. And this is a general notation that we'll see throughout the course, so it's you should remember this. So we use pi star to represent the policy that yields the maximal expected sum of rewards. So that's the target policy that we're trying to compute. G, capital G, is the observed sum of rewards. That is after one rollout in the environment. So we follow a specific policy and we observe a set of rewards throughout our trajectory. G, capital G would represent the sum of these rewards. And then we also define V star of S. This would be the expected sum of rewards from being at a specific state S and then following pi star. This will be the expected value of G, capital G, from being at state, if we start at state S. Let's look at a very specific example, a small MDP. So this is an even smaller example than our previous robot in the grid world. So here we only have 3 states, and one of these actually, we have 2 meaningful states and 1 state that is a terminal state. So this is the race car example. We have a robot car that wants to travel far and wants to travel quickly. We have 3 states for our car. It can either be cold, it can be warm, or it can be overheated, which is a terminal state. And at each state, at each of the 2 non-terminal states, we have 2 actions to choose from. One is go slow and the other is go fast. Going fast will result in double the reward. Okay, so it will give you a reward of +2 instead of a reward of +1. Okay, so the diagram here shows you both the transition probabilities and the reward function. Okay, so how does this work? So if you say, for instance, you're in state cold and you pick action fast, action here, you have a 0.5 probability of reaching next state warm and a 0.5 probability of reaching next state cold. But in any case, if you perform action fast, you will get a reward of +2. Okay? So this diagram represents an MDP. You have all of the information required for an MDP. I guess all but the start state. So let's just assume that the start state is cool. Okay, so here is a question for the audience. What is V star of state cold? So, right, you remember how we defined V star? We said it's all of the reward that you expect to see, the sum of all of the rewards that you expect to see, if you perform the optimal policy. So in order to answer this question, you might want to first answer the question of, you might ask yourself, well, what is the optimal policy? Then I'll be able to compute V star. Right, and so that would be the next question. What is the optimal policy for state cold? And here we might have, right, we can always follow, if pi star cold would be slow, action slow, what would V star be? You know, +1, +1, +1, right?
Yes.
A lot of +1s.
Yeah.
If it would be fast and then slow, let's say if it was always fast, then don't worry, we would never get warm. Then the sum will just sum +2s, right? So now that we define pi star, a bit of cheating, and that we define pi star, can we define V star? What would be V star?
V star would be the reward from the current state, which you'd get by taking the optimal action, plus the future rewards you'd get
right.
from take.
So in these cases, let's say we see +2s or +1s over and over.
So if you just keep seeing +2s and we don't overheat, then we'll just keep taking that action and we get.
So what would be V star?
V star would be 2 + 2 until how many other steps we take. So if you do it 5 times, or just doing faster. Yeah.
We'll continue driving until we're overheated.
So
never stopping.
It'll just be infinity.
Infinity, yeah. That's one. Infinity might be a bit difficult to distinguish between +1s and +2s and plus whatever, right? Okay. So this boils down to the question, which at the end of the day, we'll need to decide between what is the optimal policy. So what is a better sum of rewards, plus 1s to infinity or plus 2 to infinity? That's hard to answer, right? Infinity is an infinity. So they seem to be equally good. So what we usually do in this case, specifically for the continual decision process, is we decay future rewards exponentially by some factor. We call it, we usually call it gamma. That is a factor between 0 and 1. Okay? And now the sum of rewards, so the reward that you see at time step 0 is just the immediate reward, but the next time step would be the reward decayed by gamma. The one after it will gamma. Sorry?
Discount.
The discount rate, right. At the next time step it would be gamma squared and so on, right? The nice thing about that is that even if you continue to infinity, this is a geometric series, so this will converge to a specific value. Okay, and now if you do use a discount factor, the trajectory 2 that yields a set or a plus 2 reward over and over again is better. It actually yields higher utility compared to trajectory number 1 that yields a set of plus 1 reward. Okay, continual set of stream of plus 1 reward. And so this leads us to the idea of discounting, discount factor, which we'll discuss now. So it is reasonable to maximize the sum of rewards. I mean, in most cases we would like to maximize rewards over time, but I would claim that it is also reasonable to prefer rewards now than rewards later, right? And this is exactly what the discount factor does. It values rewards higher now and exponentially lesser as time progresses. Okay, so an immediate reward might be worth 1 at the current time step, and then gamma at the next time step, and gamma squared at the next one, and so on. Okay, so the question is, or the next question that we should address is how to actually incorporate discounting in the MDP, while traversing the decision process. Okay, so how would this work while traversing an MDP? So each time we descend one level in the expectimax tree, if you know about that from Introduction to AI, or just traversing one time step in the MDP, each time we do that, we multiply the rewards by the discount factor 1s, and over time, of course, they decay exponentially. Right? The previous rewards that we've seen many time steps ago. Why do we discount the rewards, the previous rewards? This is because usually sooner rewards probably do have higher utility than later rewards. Most people would prefer to have $10 now than $100 a year from now. I don't know if most people, but some people. Okay. And more than that, it also helps our algorithms converge. So including the discount factor provides us a lot of nice theoretical guarantees regarding convergence of different reinforcement learning algorithms. So let's look at an example. How would that work? So if our discount factor is 0.5, and we observe a set of reward that is a reward of 1 at time step 1, a reward of 2 at time step 2, and a reward of 3 at time step 3, then our discounted sum of reward would be 1 plus 0.5 times 2 plus 0.25 times 3. And once we include a discount factor, we can now discriminate between a set of reward which is 1 at time step 1, 2, and then 3, and we'll say this will have lesser utility compared to the following set of reward, which is 3 first of all, and then 2, and then 1. Right? We'll say we will prefer the second set of rewards, which provides us sooner immediate rewards. So let's look at an example and see that we understand what's going on. So let's assume a very simple grid world. It's just a corridor, And in one side of the corridor, when the robot exits at the right side, it will receive a reward of +1. And if it exits in the left side, it will receive the reward of +10. The action at each step, at each state here, between A, B, C, D, and E, the agent can perform either an action east or an action west. And in states A and E, it can perform a different action, only the action exit, which terminates the trajectory again. Okay? And the agent will exit and will receive an immediate reward that is either 1 or 10. So the rewards are only given after the exit action, and the transitions for this case are deterministic. I know I said previously in a deterministic setting we don't want to apply reinforcement learning solutions, but for the sake of this example, just to give an example of how discounting works and what would be the impact of discounting on the optimal policy. So let's start with the first question. If we'll assume a discount factor of 1, so that's a gamma of 1, what is the optimal policy? Again, a policy would be an action at each one of the states. So actually, two of these states have only one possible action, right? This would be exit and exit. Now, what would be the optimal action at state B? Trevor?
Well, since the discount rate's 1, we always prefer long-term rewards. So I think in any state, we would prefer going to state A.
Towards state A, right. So we'll take a left here, right, or confuses the direction. Is this a west or an east?
Yes, this would be right.
Let's say towards the high reward.
Yes.
And you're right. We will actually also at state D, we'll say, hey, I'm going towards the high reward, right? Regardless of the time that it will take me to get it. Because I'm not discounting my reward. I don't care if I get the reward of 10 now or 4 steps away, right? Mm-hmm. So this is indeed the answer in this case. But what would happen if we'll have a discount factor of 0.1? Now what is the optimal policy? So the solution, we don't need to have any computation, right? If we're closer to the 10, we'll try to get the 10. Also, if we're in the middle, well, it will take us the same amount of steps to get to the 10 and 1. So we should probably go left. But what would happen at state D?
Well, there would be high rewards to go right.
To go right? Why? Let's see. So if you go right, you'll get a reward of 1.
Mm-hmm. But
reward of 1, yeah. Reward of 1, but you'll have to decay it, right? It will take you 1, 2. 2 steps to get that reward, right? So it will be 0.1 times 2. However, if you
just
choose...
be, I think, 1, right? So first step...
No, so I wrote there rewards are given only after an exit action.
Mm-hmm.
Okay, so we'll assume you have to take the exit action and then... Mm-hmm. So we'll have to define it in one way or the other in order to do the computation. Okay, what would happen if you go left? You'll get a reward of 10, but it will take you 1, 2, 3, 4 steps, right? So times 0.1 to the power of 4. And in this case, of course, it is indeed more lucrative to go right. Next, for which discount factor are west and east equally good when in state D? We can compute that, right? So it will be, you can either get 10 by going left, but you'll get it only after 4 time steps. And we would like this to be equally good as getting a 1 after 2 time steps. Oops. Right? And so we solve this for gamma and
get 0.01 10 to the power.
We leave that
minus
leave that to the audience.
Or minus half, I'm not sure.
leaving this to the audience.